Now we'll introduce special cases based on the concepts of heterogeneous equilibrium. It applies to reactions in which substances are not in the same phase. In this case, we can define the equilibrium constant as a ratio between the concentration of the products to concentration of the reactant. However, we actually will ignore the concentration of any solid or pure liquid substance in the reaction medium. Any solid or liquid phase substance will have a constant concentration at all times. So we will define a new equilibrium constant that equals the product of the equilibrium constant times the concentration of any solid substance or liquid substance, which will be a new constant, right? And that will make the equilibrium constant for the reaction depend only on the concentration of the gaseous phase substance in the reaction medium. Or if you define a pressure-based equilibrium constant, is going to depend only on the pressure of the gaseous phase substance in the medium. So in general, the concentrations of solids and pure liquids will not be included in the expression for equilibrium constant for any reaction. So if we look at this question right here, we have two reactions. Which one of them will have an equilibrium constant that only depends on the concentration of carbon dioxide? So if you apply the previous rule that we just mentioned, you just ignore any solid phase substance or liquid phase substance out of the equilibrium constant expression. So if you define the equilibrium constant for this reaction, it should have been carbon dioxide times sodium oxide to the power 2 divided by sodium carbonate, right? But both these substances are solid state, so they don't contribute to the expression. We just ignore them. So that will make the equilibrium constant equals the concentration of carbon dioxide only. Same thing here. Equilibrium constant should have been the concentration of carbon dioxide gas divided by the concentration of carbon dioxide solid. But again, as we said, concentration of carbon dioxide solid is unity, it equals 1. If you substitute here for 1, it's going to make the equilibrium constant equal the concentration of the gaseous carbon dioxide only. These concepts for heterogeneous equilibria is very useful to explain a lot of special cases of equilibrium, and one example of this is the ionization of weak acids. Ionization of any weak acid, like acetic acid in this example here, is actually an equilibrium reaction that does not go to completion. It's actually going both forward and backward at the same time. So if you define an equilibrium constant for this equilibrium, is going to equal the ratio of the concentration of the products divided by the concentration of the reactants. But as we said, water is a liquid phase substance. And as we said, for any liquid phase, we will just ignore it. We will consider it constant, or we'll consider it to equal 1. So we will just remove it out of the equilibrium, and that makes the equilibrium constant for this equilibrium equals the concentration of the ions divided by the concentration of the acid itself. And generally, we don't use units for any equilibrium constant. So in general, for any acid-base reaction, you can define an equilibrium constant that depends on only the ratio of the ions to the concentration of the molecular acid itself, and it's called the acid ionization constant. It's actually a direct measure for the acid strength. So a higher ionization constant for an acid means that you have more ions than molecules of the acid, which means you have more hydrogen ions in solution, and the more hydrogen ions you have in solution, the stronger the acid will be. So just to explain how this affects the property of any acid, we will compare a solution of a strong acid like HCl with a weak acid like nitrous acid, and we'll calculate pH for both of them and compare them to each other. To calculate pH for the strong acid, from the definition of pH, it equals negative log the hydrogen ion concentration. And we can find the hydrogen ion concentration from the equation because HCl, when put in water, will completely dissolve and split into hydrogen ions plus chloride ions. So if you start with that much of HCl, it's gonna split by 100%, which means once you put it in water, you will have 0 molecules of HCl, 0.36 molar of hydrogen, and 0.36 molar of chloride. So the concentration of hydrogen ion is 0.36. So we put this in here and take negative log. So it's negative log 0.36, which will give you a pH of 0.443. In case of a weak acid like nitrous acid, it's never 100% complete ionization. So we will apply the concepts of equilibrium to explain it. So we have an initial case where you have 0.36 molar of the molecule, 0 of the ions. Apparently, this is not an equilibrium state for the system. So the system will need to change to reach equilibrium by decomposing an X amount of the molecules into an X amount of the hydrogen ions and an X amount of nitrite ion. And once it does this, it will reach equilibrium, where the equilibrium concentration is going to be the initial concentration minus the change, and it's going to be equal X for hydrogen and X for nitrite. And we will use the expression for the ionization constant, which is the ratio between the ions concentration to the acid concentration. So it's basically X times X, right, for the products, divided by 0.36 minus X. And we will make a very simple approximation here, is that X is negligible in comparison to 0.36, the initial concentration of the acid. Because typically for weak acids, the amount of ionization or the change or the magnitude of X is less than 1%. So we can safely assume that it's negligible. And that will help us simplify the calculation because it's going to give us X squared divided by 0.36, which is going to equal the value for the equilibrium constant, which is 4.5 times 10 to negative 4. And from this, we solve for X. That is going to give us 0.012 molar, which is actually the concentration of hydrogen ions or nitrite ions in the medium. So it's actually the concentration of hydrogen ions. And we can calculate pH as negative log that value, which should give us 1.9 pH. As you can see, pH is significantly higher for weak acid in comparison to a strong acid, even though they have the same concentration. So even in a pure water sample, in the absence of acids or bases, the water molecules themselves will dissociate. And this is going to be an equilibrium dissociation. It's never 100% dissociation. And we can define an equilibrium constant in this case that is going to depend on the product of hydroxide ion concentration times hydrogen ion concentration. And just to remind you, we didn't include these here because they are liquid phase substances. So they have a constant concentration that equals unity or equals 1. So the equilibrium constant for water self-dissociation will have this special symbol here to indicate that it's for water. It has experimentally has this value right here. And according to this, you can actually calculate the concentration of both of these ions in pure water, because if you start with an X amount of decomposition from water, is going to produce the same number of moles of hydrogen ions and the same number of moles of hydroxide ions. So the product of hydrogen ion concentration, which is X, times hydroxide ion concentration, which is X, is going to equal the value for the equilibrium constant, which is 1 times 10 to negative 14, which means X, or the concentration of either of the two ions, is going to be the square root of Kw, the square root of this number here, which is 1 times 10 to negative 7. So in a sample of pure water, the hydrogen ion concentration and the hydroxide ion concentration is going to equal this value right here. So as you know, we have the pH scale as a measure for the acidity or the strength of the acid. And the pH is defined as negative log of the hydrogen ion concentration in solution. So if your solution is neutral, that means that the hydrogen ion concentration equals the hydroxide ion concentration in the sample, and both of them is going to equal 1 times 10 to negative 7, which will make pH equal 7. So any neutral sample will have a pH of 7. If the sample is acidic, that is going to make the hydrogen ion concentration more than the hydroxide ion concentration in the sample, or it's basically going to make the hydrogen ion concentration larger than 1 times 10 to negative 7, which will make pH or negative log of this value smaller than 7. So any acid will have a pH smaller than 7. If the sample is basic, that is going to mean the hydrogen ion concentration is smaller than the hydroxide ion concentration, or smaller than 10 to negative 7, and that is going to make the pH larger than 7. So that gives us a pH scale for aqueous solutions, where the hydrogen ion concentration 10 to negative 7 in neutral samples, and if you take the negative log of this, is going to give you 7. And as you go to an acidic medium, you're actually having more hydrogen ion concentration in this direction, which will make the pH smaller. So the smaller the value of the pH, the more acidic the solution is. And the opposite is going to happen as you go to smaller concentrations of hydrogen in this direction in basic solutions. That is going to give you larger pH values. So as pH increases up to 14, it means you have lower amounts of H concentration or higher amounts of OH concentrations in solution or basic solution. So the larger the pH value, the smaller the hydrogen ion concentration, or the more basic the solution will be. And we can actually define a P function for the OH concentration in any solution to equal negative log of the hydroxide concentration in the solution, but the concentration of hydrogen times the concentration of hydroxide in any solution will equal this constant right here. So if we take negative log of the whole equation, so negative log of the hydrogen ion concentration, negative log of the hydroxide ion is going to equal negative log of 1 times 10 to negative 14. So basically, this here is pH, this here is POH, and this here will have a value of 14. So the sum of pH plus POH will equal 14 in any aqueous medium. And that is very useful to just measure the alkalinity of a solution depending on pH only. You don't need to have a special meter for pOH. And that allows us to apply equilibrium conditions to weak base ionization. So that example here, the ionization of ammonia, is an equilibrium reaction with an equilibrium constant of this expression right here that is called the base ionization constant. And again, it's basically the ratio of the concentration of the ions to the concentration of the base itself. And again, it's going to be a measure of the strength of the base. The larger the ionization constant means you will have more hydroxide ions in solution, which will make the base stronger. And we will do the same problems like we did weak acids, except we are solving for hydroxide ion concentration in this case. So for example, if we compare the pH of a strong base solution like NaOH to a pH of a weak base solution like ammonia, for the strong base solution, if you put NaOH in water, it's gonna completely split into Na plus OH minus. So once you put the 0.4 molar solution into water, it's gonna completely convert to 0.4 of Na and 0.4 of OH minus and leave 0 of the base itself. You can calculate pOH for the sample by taking negative log of 0.4, which will give you of 0.4, but we can calculate pH of the solution by subtracting the pOH value from 14, which is gonna give you 13.6. So that's the pH value for the strong base solution. For the weak base solution, an ammonia solution, this is a weak base, so it's gonna basically split according to equilibrium principles. So it's gonna make NH plus OH minus, and you start with the initial condition of 0.4 molar of the molecule, 0 of the ions. The system obviously is not at equilibrium and needs to change by splitting an X amount of the molecules to make an X amount of ammonium ions and an X amount of hydroxide ions. And when the system reaches equilibrium, is going to be the initial concentration minus X. And this is going to be X and this is going to be X. And the equilibrium constant is going to equal the ratio between the concentrations of the ions divided by the concentration of the base at equilibrium. But remember, we said X is negligible with respect to the initial concentration, so we just can cancel it out. And that will make the calculation significantly easy, because from this, you can calculate X, which is gonna equal the square root of 0.4 times KB. And you just use the value for KB from here, and that is gonna give you the value for X, which is 7 times 10 to negative 6. And that is the equilibrium concentration for hydroxide ions. So you basically can use this to calculate pOH for the sample. It's going to be negative log the hydroxide ion concentration, which is supposed to be 5.1, which will make pH equal 14 minus pOH, which is 5.1. So it's actually 8.9. See how weak your solution is. You compare the pH of that solution with the sodium hydroxide solution pH, which is significantly higher, which means it's significantly more alkaline.